Alright, so we're going to be looking at forces using the force tables, and we're going to create the forces by putting mass on hangers. We're going to be looking at, well, back up. Force is a vector, and vectors we said have two things. They have magnitude and direction. So we're going to look at how we can determine the magnitude and direction of a force experimentally, but we're also going to look at how we can figure it out analytically and graphically. So with math and with a graph. Okay? And we're going to see how a resultant is related to an equilibrium. And we'll get more into that as we get into the lab. But one thing I need to go over with you before you start is you're going to be given forces, but you're going to have to create the force. The only thing you have at your desk to create a force with are those little mass sets, okay? Force's unit is newtons. What is the unit for mass? Grams or kilograms. We have it in grams, but we need to know in kilograms because kilograms is what goes in our formula. Okay, whenever you're talking about force and you're talking about mass, you want it to be in kilograms. So there is going to be some converting going on. But what you're going to do is you're going to be given a force in newtons. The formula to get force, to get mass from force, you're going to have force equals m times g. What is g? The gravitational acceleration. Usually it's 9.8. For ease sake, today we're just going to round that to 10. Okay? Just for ease of math, and so we don't get caught up in that, we're just going to round that to 10. So for example, if the lab tells you to create a 0.5 Newton force, I'm going to plug that into the formula here. 0.5 equals mass times g. I plugged in 10 for my g, and I get my mass as 0.05 kilograms. Okay? But my mass set that I have, that's in grams, that's not in kilograms. So then you need to convert that to grams, and you see that 0.05 kilograms is going to equal 50 grams. So that tells you that I would have to put 50 grams hanging to create a force of 0.5 newtons. Y'all follow me? Yes? Okay, but here's another kicker. That hanger, that mass hanger, is 5 grams itself. So if I need 50 grams hanging, how many grams do I need to put on the hanger?
45.
45. Okay? So you want to include the hanger in that mass. Okay? Because I believe it says on the hanger that it's 5 grams. Okay? Any questions so far? Alright, so we're going to do case 1. And if you look, case 1, I need to write that on the board because I don't think is that on your paper? Let's see. It is. Alright. Well, first, before we do case 1, look at the pre-lab challenge questions. Number 1, when drawing a force vector to scale, what information must the vector convey? What two things must a vector convey? Magnitude and direction. All right, number 2. It says two forces are pulling on a point, see below. Draw a vector to indicate the direction the point would move if it is movable and estimate the magnitude of the resultant force. What it's saying is it's giving you a horizontal vector of that 1 Newton, and it's giving you a vertical vector of 0.5. Where would your resultant be? If you've got two things pulling, one's vertical, one's horizontal, which way is the resultant going to be? Where is the combined force of those two going to be? And it may be easier for you to visualize it if you put that vertical force, not that it matters, think back to our map, it really didn't matter, but if you put that vertical force on this side, where's the resultant going to point to when you combine those two vectors? As far as, do you think it's going to, the problem gives it to you like this, correct? It gives you 0.5 newtons, and it gives you 1.0 newtons. It says it's combined. So for us, sometimes maybe we visualize it better. It doesn't matter if we put this 0.5 newtons on this side. It's still a vertical. But which way is our resultant going to be? Okay? If I'm pulling up and over, then it's probably going to go diagonally up to the right. But how far do you think it's going to go? Do you think it's going to go more straight up? Do you think it's going to go more like this? Do you think it's going to be flatter? Where do you think that line would be? I want you to just draw a line of where you think the resultant would be in that number 2 question of those two forces. Okay, so now we need to set up our force table for the first case. All right, and we're going to make sure that we predict, after we get it set up, we want to make sure that we make our prediction before we get into working anything out. So in case number 1, you've got 2 forces. We're going to call them A and B. Force A and force B. It's going to be at 0.5 newtons at 0 degrees, and it's going to be, B is 1.0 newtons at 90 degrees. Okay? The first thing you need to do is figure out how much mass this is going to be using this. How much mass that's going to be. And then, if you look at your force table, let me turn this way. Got their math hangers out. Up there. Let me see your math hangers. On your math hangers, you'll see. So here's a math hanger. There's a paper clip on the end. Where's your white ring? So what you'll do is your white ring goes in the middle of the force table, and you'll take your paper clip and you'll hook it onto the white ring. Your pulley. Then you'll put your pulley on the force table. You notice you got degrees on your force table. So I'm going to put one pulley at 0 degrees. Make sure you line it up. There's a little indentation there in the pulley where you can center it up. And then since the other one's at 90 degrees, I'm going to take another pulley and I'm going to center it up on 90 degrees. And then I'm going to figure out the masses for each one, and that's what I'm going to hang on these mass hangers. The thing about the pulley though, you want to make sure that that pulley, that the string is level. You don't want the wheel of that pulley to be too far up or too far down. You want it to be level, okay? And once you find the mass, you're going to hang it on the mass hanger. All right, so you have your force table set, and you have your force, your 0.5 newtons force is at 0 degrees, and your 1 newton force is over here at 90 degrees. So the first thing I want you to do is look under the XY axis for case 1 where it says sketch your educated prediction. Your goal here in this lab, see the white ring in the middle? Your goal is to where you can put a force on this that's going to center that white ring around that post, where that post is completely in the center. And you want to see what is going to be the resultant, predict what degree and what force it's going to take to center this ring. What degree and what force is it going to take to center that ring? Okay, and that's what you're going to draw. Okay, so your 0 degrees on your XY axis would be to the right at 0 on the x-axis. Your 90 degrees would be straight up. Where is your force going to be that's going to center that ring? Make a predict. You're just making a prediction. That's all you're doing. You're making a prediction. Draw where you think it would be. There's no wrong answer. It's a prediction. If you say that, let's say that to even out your ring, here's your 0, here's your 90. Let's say that you predict it to be this way, to even it out. This is actually going to be what's called your equilibrant. And your resultant for that, the opposite of equilibrant, is going to be the actual resultant, which is that way. How many degrees is the difference here? 180, okay? So listen, whatever you think and you predict that's going to pull that ring to even it, that's going to be your what's called your equilibrant. Listen to me now, and the 180 degree difference is the resultant. So what you are writing in the chart as your prediction, make sure that you go ahead, you should see the word prediction in the chart. Make sure you put the resultant and the prediction. But you want two things in that. You want the degree that you think it's going to be and the mass that you think it's going to be. Okay? And it's just a prediction, so it's okay to be wrong. Now, under that, once you've made your prediction, you're going to actually experiment and try and put on a third pulley and a third mass hanger, and you're going to start trying to get that ring evened out in the center. Okay? Does everybody follow me? Yes? Yes? Okay. If not, I'll come to your table. So make a prediction. The result, the equilibrant's this way. The resultant is this way. Make a prediction and then do an experiment to see what it actually is experimentally.
To be fair.
All right, here we go. We're filming. Okay, so remember, this is, with case 1, you put two forces on your force table. You put the 0.5 newtons at 0 degrees, and you put the 1.0 newton at 90 degrees. This is going to be our force A, which is right here in our chart. This is going to be our force B. If you're virtual, you probably need to pause the video and copy down this chart real quick. Remember that this Greek letter sigma means the sum of. So what we're going to do is we're going to get the x for both forces, add them up, and we're going to get the y for both forces and add them up. Remember your terminology. Resultant is going this way with these forces. The equilibrant is 180 degrees opposite of that, this way. All right. So what is the x? And it's going to seem a little pointless. Why are we doing all this work when we know there's no y, like the y is 0 right here and the x is 0 here? But what I'm doing is I'm training you with this easy one to be able to see how to do the next one, because the next one has a force A, a force B, and a force C. So instead of two vectors, starting with two vectors, we're starting with three vectors in the next case. So I'm training you with this one, okay? Because some of it might seem pointless, but I'm trying to set you up to be able to do the next case, okay? Alright, so if we're looking at angles and X's and Y's, and we want to get an analytical evaluation of what this angle is going to be right here. So let's make this our theta. What do we need to use? What functions?
Cosine.
Sine or cosine. So that we're looking at more of those trig functions, okay? Alright, so we're going to start and just focus on force A right now, okay? So force A is this 0.5 newtons, alright? And so we're going to write that force A, and we're going to break it down, because remember, vectors can be broken down into two parts, right? The X component and the Y component. So we've got F, force A, and we're going to look at the X component of force A. Alright, so we're going to look at the X component of force A, we're going to look at the force times the angle of A. So we're going to look at force times the cosine of theta of A. Now, why are we using cosine with this? Opposite would be with this one, but this side is adjacent to theta. So we're going to say force of A times the cosine of A, and then we're just going to plug in, and we're going to have 0.5 newtons. That's our force. That's our force of A. Times the cosine of 0. So do that in your calculator. Do the cosine of 0 times 0.5. You get 0.5. And that's going to be a force, so we're going to go with newtons. So the X component of the force of A of this one is 0.5 newtons. Well, you could have told me that without going through all that math, but what happens when this is not a straight line and it's not going at 0 degrees and it's not so simple? Okay, so this is what I'm doing. I'm setting you up to, this is part of setting you up to be able to figure out the next one. All right, so let's go with the Y component of this force. Now, before you even work this out, okay, this is using common sense. What is the Y component of this 0 degree line right here, 0.5 newtons? Is it going anywhere up in, Y is vertical, right? Is there any vertical motion in this line? So what should our answer come out to be at the end? Should come out to be 0, but let's see how we're supposed to work it out and make sure that analytically with this math that it comes out like that. So we're going to do the force of A. Now will we use, we're going, we want vertical. There is no vertical with this one, but we want to do sine with this one because we want the vertical angle of Y, so we're going to do sine of theta of A. So let's just plug in, and we're going to get our force is 0.5 newtons times sine of 0, and do that in your calculator. For the vertical one, we're using the sine. And tell me what you get. Do we get what we expect to get?
Yes.
0. And that's what we expected to get because we can look at this and see there's no vertical component. All right, so that is the A force, so our first one, but it's the Y component. So that's gonna be a 0 right here. All right, so let's look at B real quick. We've got F, B with the X component, and then we're gonna do FB with the Y component. All right, so we're gonna do FB, and with the X, we're gonna use cosine. So we're going to do cosine of theta B. What is our degree in B? Our second force. What degrees are we looking at? 90. We're looking at 90. All right, so we're going to put in our force. What is our force for the second one? 1. All right, so we're going to do 1 Newton, plugging in for our force, times horizontal, we use cosine, and we're going to use the angle here, cosine 90 degrees. Now, before you do this, what do you expect the X value of this line to be? Zero. There's no horizontal motion in this force, is there? It's a straight up vertical force. We expect it to be 0. Is that what you get when you do that in your calculator?
Yes.
Yes. Okay. So that's going to be a 0 newtons. So force B, the X, is 0 newtons. Now remember again, yes, I know we can look at that and we can tell that, but I'm setting you up for case 2 so you'll know how to work it out. All right, so let's look at the Y. We'll take force B, Y, the vertical, we're going to use the sine. Sine of theta B equals, our force is 1.0 newtons. Times, and we're using sine of 90 degrees. Now, what do you expect it to be? What do we expect our vertical force to be?
1.
1. Is that what we get?
Yes.
And we get 1 newton. Okay, so our Y value here is 1 newton. So if we add those up, our X component for our force, for our whole thing, is going to be 0.5 newtons. We just added our X's up. Our Y component, you add those up and you get 1.0 newtons. Well, we knew that because we can look at that and tell that. And this one is set up where it is 2 straight lines, 1 horizontal, 1 vertical. So it's easy to tell that. The next one's not going to be like that. So that's why I wanted to show you the process with this one. Okay, so now that we have the sum of our forces, do y'all have all this written down? Yes? Okay, I'm going to erase this so I have room to work and it is still on video. So now we want to figure out the force of this resultant and the angle that it's at analytically, which would be, because we're doing a vector, doing vectors, force is a vector. What 2 things does a vector have?
This was the magnitude.
Magnitude and direction. Magnitude and direction.
That's what you did for coffee.
Okay, so if I know these two sides, how can I find this? How can I find the hypotenuse? Not the angle, the length. How do I find the length?
A squared plus B squared equals.
There we go. Okay, so I'm going to take a square.
We're doing so much difficult things that my brain doesn't realize they're easy.
A squared plus B squared. It shouldn't have been that simple is probably what you were thinking, right? Okay. All right, so we're going to do a squared plus b squared equals c squared. We know our x component and we know our y component, so we're just going to plug those in and we're going to get 0.5 squared plus 1 squared equals c squared. So 0.5 times 0.5, you got 0.25. 1 square, you got 1 is equal to c squared. So 1.25 is equal to c squared. What are you getting for c?
1.12.
Okay, so c is equal to 1.12. So I know that mathematically the force of my resultant should be 1.12 newtons. Should be the force of my resultant. What did y'all get experimentally as the force of your resultant?
1.12.
Some of you got maybe 1.05.
Yeah, I got 1.05.
Did anybody get 1.10?
I got 1.15.
Okay. Okay, so now let's take it a step further. All right, we need to find theta here. We need to find theta. What can we use to find theta? Sine, cosine, or even we can even use tangent now because we know what our resultant should be. So let's use tangent. Tangent is equal to opposite over adjacent, correct?
Yeah.
All right, so that would be, if we plug in, opposite is 1 over 5. Point 5, my bad. 0.5. 1 over 0.5.
Oh, just kidding, no, I didn't.
Yes, you did.
Did I? I don't know, I didn't put tangent. Oh, this is
I didn't either.
I got a 0.3.
Oh, did y'all do the inverted tangent?
No, that's a normal tangent.
Hold on, let me
Do the to the -1. Do the inverted
Okay.
in your calculator.
63.43.
63.43.
63.43. That's what you should be getting.
That's not what I got.
Look at your angle that you said you had for the resultant experimentally. What was your angle experimentally?
61. 67.
Oh, so we're close.
Smart people.
So if this is my resultant, so in your box on your chart, that data table at the bottom, where it says the resultant analytical for case 1, you're gonna have, for the analytical for case 1, you're gonna have that 1.12 newtons at 63.43 degrees. That's what you're gonna have in that box. That's for your resultant. So if that's the resultant, how do I get the equilibrant? It's opposite.
So would you just
From 80.
I'm gonna add 180 to 63.43. So to,
because it goes all the way around.
right, because it goes around, and so I'm gonna take that 63.43 plus 180, and I'll have 0.43. I should get 243.43. So your equilibrant is the same force, but in the opposite direction. That's your analytical. A lot of steps, I know.
Come back tomorrow.
And it stays at 112?
Yeah, it's gonna stay at 1.12.
Oh my goodness, I forgot meat spaghetti.
What's today?
It's just for Cameron. It's just for Cameron.
I'm gonna take it down once they finished.
That was close to mine. I did at 247.
So that's not far away then.
I'm like 2 away each time.
Can I
Was
look
I
at this?
150 or 115, and then I had 241 and 61.
We were decent.
All right, we'll stop the video, I think.